So let's get started. So this one is actually a talk that's pretty important to me. We're going to talk about the differences between the UTXO model and the accounts model. And it's important to me because other than PBA, the thing that I work on as a blockchain professional is a UTXO system for Substrate. And actually, Andrew and I built this thing together. It's called Tuxedo. And normally Andrew gives this talk, but this time we decided to swap a few of them. And so I'm giving this one this time. So it's my first time actually giving the talk. And as always, I'll just encourage your questions and engagement. So the main thing that we're talking about here is multi-user state machines. So I know that we practiced a lot yesterday modeling and designing relatively simple state machines. We talked about like our audio amplifier, for example, or the light switch or whatever. Now we want multi-user state machines where users can interact with each other. So maybe as a first step, don't think about just an audio amplifier with 3 buttons and 4 volume levels, but maybe think about like 1 amplifier per person. Like we each have our own little audio system and we want to build a state machine that can model that. And maybe without too much trouble, you can sort of think about how you'd model that. Maybe you have like our same diagram that we had before, with all of our states, except that now you have this many states times however many users there are. So if there's like maybe 10 users, then instead of having these 7 states, you would have like 70 states or something like that, or the outer product of the states actually. And so by the time we get to a multi-user state machine, it's hopefully pretty clear that we definitely are not going to be drawing like complete state space models anymore. That would be crazy, especially because it's not actually just giving everyone an amplifier. That's cool. But the real power and beauty of the blockchain comes from allowing the users to interact with each other and affect each other. So think about things like taking the output of my amplifier and plugging it into the input of your amplifier to get even more sound or something like that. Or to use like the most obvious currency example, it isn't just I take some of my coins and burn them, or I like dig up some gold and make new coins. It's the really interesting parts are when I'm sending coins to you or you're sending coins to me or her or them or whatever. And so that's what we're going to start to do now. And there's basically 2 ways to do this. I should say there's 2 very popular ways. It's not the case that these are like the only 2 ways or that we have some proof that there's exactly 2 ways to do this. There's others. I've heard of like the actor model, for example, and I'm sure there's other esoteric ones that I just have never even heard of. But by far in like production blockchains, these are the 2 most popular models, and so we definitely want to understand them. And so then you'll know the biggest 2, and you'll also know how they can differ and everything, so you'll be well prepared to understand any new model that you encounter in the future. So let's start, so let me just say what they're called, accounts and unspent transaction outputs. So this one is what we are talking about when we say UTXO, and there's no X in there, I get that, but it's like from the transaction. So I'm gonna go through the UTXO model first, and this is sort of the one that appeared on the blockchain scene first. So the UTXO model is what you'll find in Bitcoin and in Dogecoin and Litecoin and Monero and all of those OG, like 2011, 12, 13 tokens that were all copies-ish of Bitcoin. They all use the UTXO model. And what I'm showing here is an example of a state. Now this diagram looks kind of similar to what I have on the board here where each box represented. Each box was a state, but that's different up here. What I'm showing up here is a single state. And in the UTXO model, within a single state, you have all of these individual little chunks of state, these individual little pieces, here's one, here's one, here's one, there's one, here's 4 more. And each one of those is called an unspent transaction output. You know it's unspent if it's in the state. Only unspent ones go in the state. And then if I send some transaction that mutates the state, then what we'll do is we'll take some of these and we'll spend them, and by spend, that basically means you consume them, you get them the heck out of there, and each transaction will also put some new unspent transaction outputs into the state. So in the UTXO model, each piece of state is local. There isn't like one place where you know that every piece of state will be. For any individual piece of state you want, you actually might have to do a little bit of work to find it. So let me give you an example. Let's say that you want to know my balance. Like, how many tokens does Joshy have? There's no one piece of state. It would be incorrect for me to look at this top box and be like, oh, you want to know how many tokens Joshy has? Okay, well, I found this piece of state that says he has 30. I guess he has 30. Can anyone see the problem? Yeah, like this one, for example, or this one. And so the complete picture of what my balance is actually scattered throughout the state. And so in order to come up with the total balance, you might have to do a little bit of processing or a little bit of searching, or you might need to have a little bit of additional information, such as which ones of these UTXOs belong to Joshy. In the end, this is the way we do it. We find all of the ones that belong to me, and then we just sum up their values. Now, one way we could do this is to iterate over the entire state space and just filter out the ones that belong to me. Obviously, that would be fine when there's 8 pieces of state, when there's 8 UTXOs. That would never be efficient in the Bitcoin blockchain. And so, in fact, the way that a UTXO wallet typically handles this is that it starts, a UTXO wallet buddies up with a node. It contacts a node over an RPC endpoint. And then every time the node gets a new block, the node says, hey, wallet, here's the new block. And the wallet looks through that block and it says, hey, does this block create any new outputs for Joshy? And if so, let me just note them down here in my little local file that keeps track of them all. So in the UTXO model, the wallet actually has to be following the blockchain block by block so that it can check any moment when, for example, I get some new coins. Or if I spend some coins, then the wallet needs to notice, oh yeah, these coins got spent. We need to remove them from our little list of relevant pieces of state. And so if you think about your wallet, basically what your UTXO wallet does is it tracks a subset of the entire blockchain state. And specifically, it tracks the subset that it considers relevant to you. So in the case of my wallet, it would track these 3 tokens that are relevant to me. And meanwhile, Pauline's wallet only is tracking this one, and Cartman's only this one, and Andrew has, these ones over here. Oh yeah, sorry. Let's get a mic up here.
So would it be possible to create a transaction that spans more than one output transaction and create a new one, so you could join all the 3 Josh into a single one to make it more efficient to find?
Yeah, absolutely, absolutely. So in the UTXO model, each transaction, what the transaction is it's a list of inputs that it wants to consume, and it's a list of new outputs that it wants to create. And when you send that transaction to the blockchain, it does some validation. Just to stick with the money example, it makes sure that I'm not creating more value with my new ones than I'm consuming with my old ones. That would not be a sound money. But assuming all of the state machine specific checks are made, then it puts all of the new outputs into the space. And so to answer your question, absolutely, transactions contain a vector of inputs, which are the ones you're going to consume, and a vector of outputs, which are the ones you're going to create. And so it would be totally valid for me to come here with my wallet and say, hey, wallet, build me a transaction that sweeps up all of my UTXOs and creates a single UTXO that has the same value. Yep. And then that would simplify the state space. Was there another one? No, okay, cool. So next thing I want to talk about a little bit is addresses. So we see here actually, let me pause for 1 second. I want to be sure I have the latest version of my slides. Okay, all good. So I want to introduce this notion of addresses. So far I've kind of explained it conceptually, and you can see here the owner is, this human readable English string. Of course, that's not how it works in the blockchain. And so what we do is we leverage some of the tools that we learned about from Saeed back in week 1. Specifically, we're going to leverage public key cryptography. And so instead of representing users by their human readable names, which aren't really very structured and can collide and have a bunch of other not very computer-friendly properties. Instead, we're going to represent them with some kind of cryptographic identifier. So you might think of this as the public key. That would be a pretty straightforward way to do it. Instead of writing my English name, we'll write my public key. That would work totally fine. Another thing that people commonly do, this is what happens in every major blockchain, is they have an idea called an address. And the address is basically just the hash of the public key. So if you want to know what your Bitcoin address is, you generate a key pair, you take the public side of that, and then you hash it, and then that's your public address. And the idea then is that we get an address that's unique to each person. And when I say unique, I'm invoking all of the properties you learned about hash functions and how they're collision resistant and that kind of thing. Okay, so let's consider if we want to send some money. Let's say we want to take some of my tokens and I want to send them over to Andrew. I want to give him some value transfer. Maybe I'm trying to buy his car. Maybe I'm trying to buy his car so that I can later double spend and rip him off and keep his car. Or maybe I'm just trying to buy it like a normal person. And so what I need to do, like when I was answering your question, is I need to tell my wallet which ones of these I want to consume. And so this brings us to the idea of an input. I mentioned that transactions have inputs and outputs. And so let's just pretend that out of all of the state up here, this is the one that I want to spend. I feel like there's some echo on or some ringing maybe. Okay, and so when I go to build my transaction, I need to show, obviously, like, I can't just go spend this coin or this coin, because that one belongs to Pauline, and a good blockchain will prevent user X from spending user Y's money. Oh yeah, should I try a different one? Yeah, we'll see. Seems fine, thanks. So here's how an input looks. The input itself is the pink box, okay? What it has here is a signature, my cryptographic signature from my public key. Okay, that part probably doesn't surprise you. You're always gonna have to sign to spend your money. And then the other thing it has is an ID. You can think of this as like a UTXO ID, some kind of unique identifier for each UTXO that's in the state. Now the input itself doesn't actually contain all of this data. That's why it's not in the pink box. It just references this data. That's what the arrow means. By using this ID number 6, we're specifying the unique UTXO ID that I want to spend, and then we're providing a signature. And of course, when we send this thing to the blockchain is going to check. What the blockchain will do is it will look up UTXO ID number 6. It'll say, okay, who owns this thing? 0123. And who signed it? Here's the signature. And so they'll check that that's a valid signature that comes from the correct owner. And if it is, then at least this part of the transaction validation succeeds. Okay, so let me pause there. Yeah, question, great. Throw the mic up front, right here, throw it up here. Right here, raise your hand, yep.
Thanks. So I used to contribute some things, comments to Bitcoin. I haven't touched it in a long, long time. And I think for building Ethereum wallets is relatively easy. I think you just have RPC calls, etc. But I'm wondering, in terms of someone wanted to build their actual software wallet for Bitcoin, does that mean that they have to connect to a few different services that will go ahead and essentially index or listen to transactions for particular addresses, or how does that work
in
practice?
You're thinking about it. So your question is like, if you want to build a Bitcoin wallet, right?
Yeah,
like
exactly.
Maybe you get the concepts, but like, how do we implement this thing? Well, I love the question.
Back in the days, you had to run your own essentially node, right? And you had a software wallet.
Yeah, so back in the day, the wallet was built into the node. It doesn't have to be that way. They can be different pieces of software. But with any blockchain wallet, no matter what model, it always needs a node to communicate with, whether it's accounts or UTXOs. But your question has something very good. It's like, this seems complex, right? We're scraping the blockchain looking for new outputs. Whereas Ethereum, you can kind of call up the node and say, hey, node, what's my balance? And it just tells you, because it's at one specific place in storage. And so the jobs that you're describing, they're best done by your wallet. Those are the things that your software wallet does, the indexing and everything. So if you've ever spun up a Monero wallet, for example, you have to sync your Monero node, just like always, download the blocks and everything. And then you have to sync your wallet to the node. And that's a much faster process, although it still takes some time. The wallet will go through and scrape the blockchain and look for any UTXOs that you have in the blockchain. You sort of proposed a design where maybe you rely on some other service to do that, which would be fine, except, the trustworthiness part. Yep. Yeah, great question. All right. So let's look at some transactions, or a transaction now. We already told you about the input side, right? Here's the input, it looks exactly the same as before. Now here's the output side. This is the part that I'm sending over to Andrew. You can see that I put his public key here. We have some new like UTXO ID. In this case, we're just treating it like a serial number, like every bill gets the next number. And you can remember that I had like 8 little UTXOs in my example space. Now I'm creating a new one, so this is number 9. I'm consuming number 6, and I'm creating number 9. And so again, the transaction here is the blue and pink boxes. The pink is the input side, and the blue is the output side. The green is not actually part of the transaction, it's just being referenced. This is part of the blockchain state, it's just being referenced by the input here. And this is a pretty simple transaction, has one input and one output. It could have many inputs and many outputs, or it could have many inputs and no outputs, or one input and 4 outputs. So in the UTXO model itself, just the pure UTXOs, there's no limitations on how many inputs or outputs you need. Now, if we're going to talk about money, you can probably infer one kind of limitation, like you're always going to need at least one input for money, right? You're going to need money coming from somewhere. But in general, if we're talking about like a voting app or like a CryptoKitties kind of thing, there's no requirement. It could be 0 inputs, could be 0 outputs, pretty flexible. Okay, let's throw the mic right here.
Why ID 9 on the right side?
So in this case, it was just like the next serial number. We're just doing them sequentially, and there were 8 of them before in my space, so this is like the 9th one. This is like a little bit of a simplification. It's in reality, it's usually not just a serial number. It's usually like the hash of the transaction, the hash of the entire transaction, and then like the index position that this thing has within the transaction. So you could think of like, if we pretend this is a real world blockchain transaction, I take this whole blue-pink thing, I throw it through my SHA-256 or whatever hash function, and then I say, okay, this is the 0th output in this transaction, so I just like concatenate a 0 onto the end.
And so the way that this relates to the previous, like when you had like the 8 transactions, which are bundled in one block, if I understand correctly, then...
This, you mean, yeah?
Yeah, so, what is your one?
Sorry, what?
No, I'm just counting yours, but
Oh, yeah,
looking
yeah.
for yours. 1, 2, yeah, okay, so basically like, what we just saw before, like in the forward slide, that's the sum of these? Or is
It's not the sum. It's like they literally just have IDs, like 1, 2,
Okay,
3, 4.
So each one of those is a transaction?
No, they're not transactions. These are UTXOs. These belong in the state. Okay, so let's zoom out a little bit. Forget about UTXOs for a second and think about state machines. You have a state, and then you make a transaction, and that takes you to a new state. And then you make a transaction, and you're in a new state. Okay, so this whole thing that's on the screen right now is a state. And each little UTXO is one little like piece of that state, for example. So then, when I go to make a transaction, it's going to be this blue-pink thing right here. Okay, so it's going to take me from that previous state that had 8 boxes to this new state right here, which you can see 6 is no longer in there because it got consumed. And now 9 is added in here. So this is our new post state. Oh, everybody's a critic. Andrew made this slide. I'm just kidding. Yeah, that is just a typo. It should say 65. So let me say it for everybody. Like my output here in the blue box, it says, oh, you can't see my pointer, I guess. It says 65 there. So in here it should have also said 65. Wow, I love that you noticed that too, baller. Man, that's some good attention. Yeah, go ahead. Get the mic.
Sorry.
Oh, you have it already? Okay, all right. Yeah.
Sounds good. If you go to the next slide, and then, so basically we're coming from this current
Hold on. Which one do you want? This one?
Sorry,
Oh,
the
wait,
small one.
hold on. This one?
Yeah. So the pink box is basically a transition, right? Transaction state, some sort.
The whole blue-pink together is a transaction.
It's a transaction.
Together they make the
It's
transaction.
basically like changing one static state
Yep.
dynamically to another static state.
Yeah, yep, exactly. So
that's-
just like every state machine, it takes some input state, which is the slide with 8 boxes up there, and then we do this transition, and then we get an output state, which is the slide with 8 boxes, but they're not all the same boxes as before. Yeah. And so, you know, like and I love that you guys are digging in and now you're giving me ideas for how I could have done this even differently. You know, let's say I could have had like my pink input here consuming this thing, and then this blue output for 65, and then maybe like another blue output down here for like 2 tokens. That's okay, that still only adds up to 67. It's less than I consumed originally. And so when we get to the post state, then we would have, you know, here's the one for 65, and then here's ID number 10 that has those additional 2 tokens or whatever. Did you want to go still? All right, throw the mic up here.
If the input value doesn't add up to the output value, aren't you like burning tokens or something?
Yeah, yep, that's exactly right. So in the way it typically works in a cryptocurrency, the like cardinal rule is that the input value has to be greater than or equal to the output value. And in the case where it's not equal, where it's greater than, it's like what happens to the rest of the coins. And so like in Bitcoin, they go as a reward to the person who mines the block, but maybe you want to burn them or put them in the treasury or any of those other interesting things that Jonas said. But they don't go into like one of the recipient like UTXOs. They certainly don't like remain in the original UTXO with like a different value. So that's one thing we should be very clear on. You never ever mutate a UTXO. You only destroy them and create new ones. And so a common thing is like, let's say you're gonna sell me like a piece of bread for like 50 tokens, but I only have a UTXO that's 70 tokens, and I don't want to burn 20 because that's too much, like it's more than I want to waste. A lot of times what you'll do is you'll build your transaction so that like I consume my one that's 70, and then I give you the price of the bread, which is 50, and then I create another UTXO back to myself. It still belongs to me, and it's called like the change one. You know, it has like the difference in it. Yeah, go ahead.
In a single transaction, can I spend you text those from more than one wallet with a multisig or something?
Yeah, you can. So let's look back here. So this is, let's say this is like my input state right here. And we already talked about how it's easy for me to like spend 2 of, you know, my UTXOs. But let's say that maybe like me and Andrew are like pooling our money to go do something. We can construct a transaction that takes like one of mine and one of his, and we both produce the correct signature, and then they can both be consumed within a single transaction. And one very common way that happens is that it might not be 2 different like unique human owners. It might be that I like made this address one day and this address the other day, and now I'm gonna sign with the 2 different keys that are both mine. And the cool thing is that the blockchain really has no idea whether it's me and my other wallet, or whether it's like me and Andrew, or whether it's some complex like, you know, relationship between companies or something like that. Carla.
When you say you destroy them, I'm just trying to understand it. They're still there because as a result of immutability, you can find them. That's
so
the whole point.
they still show up in the history of the chain. So what's immutable about the blockchain is the history. You can't go back and change the shared story. So what you can see is like, oh yeah, once upon a time, Joshy owned these 70 coins, and then he sent some to Andrew. That's all still accounted for. So what I mean when I say destroy them is I mean they're no longer present in the new state, in the output state.
Thanks.
Yeah, great question.
All the time I'm trying to understand, maybe you can answer this later, but I'm just putting up the question. What are the advantages we get by going into this model, which seems more complex? So that's
More complex than what? This is the only one we've talked about.
Yeah, so,
So
in
just
right time
asking a little
complete,
bit. And actually that's in the slides too. Thanks for the question. So I wanted to, let's see if we covered all of this already. Okay, yep, we have to do the signature verification. And so I guess, you know, like just to say this like one more time, if we do pretend there's a transaction here that has like this input from me and another input from Andrew, obviously we need to verify the signature on each and every input, and we need to verify that the signature matches the owner on each and every input separately. Yeah, there's this thing like a good UTXO cryptocurrency has this rule that no coins can have a 0 value, because otherwise I could make a transaction that like consumes my 1 Bitcoin and creates like 10,000 outputs that are all worth nothing, and that would obviously like bloat the state space like what? I mean, honestly, even this isn't good enough. Like it should be no coins are worth less than 1 or less than 0.00 or, you know, whatever threshold you like, because otherwise your state bloats. Let's get a mic on the back there. Yep, put your hand up again. He's going to throw it. Right there. His hand's up in the back. Chuck it.
Yeah, Marisha. So can you go back to transaction input and output? Yeah, sure. The owner or 042. So the output transaction has
It's
a
an
new,
output UTXO. The
UT
whole thing here is the transaction.
yeah, the whole thing is a transaction, yeah. But then the last state, the output,
output
there,
UTXO.
yeah, it creates a new owner. Like why?
Because when I buy your car, you need to be the owner of this new coin. This is an example of when I want to buy something from you and you say the price is 65 tokens. So it wouldn't make sense to send those 65 tokens to myself, right? I need to send them to you, and then you're going to give me like whatever thing I'm buying.
Okay, and also like okay, but then okay, I was having 70, right? The five remaining, it also creates another output, right?
So in this case, no, it doesn't. In this case, it's just going to get burned. But it would be perfectly valid, like if I really care about that 5, for whatever reason, maybe that's a lot of money, or maybe I care about every little cent, it would be perfectly fine for me to make another output in here that's owned by me and sends those 5 tokens back to me. This particular transaction doesn't, but you can.
So honestly, the UTXO state machine, you can say in terms of transaction, it's just manipulating the owner, and it's like this state, the coming state will have another owner with the difference of tokens and everything, and you can just output many number of outputs, right?
Yeah, absolutely. Yep, exactly right. And the constraint, of course, is that like however many new coin values I'm creating, obviously the old ones that I'm consuming have to be equal or greater. Oh yeah, right. And so like, one thing that you need to check, of course, is also like, has this input been spent before? If I send a transaction, it has something as an input, we need to make sure that that input is actually existing in the pre-state, right? You can't just list any input you want. Anything else here? There's a note in the speaker notes that said, which one did I forget? Is there any I forgot? Any I forgot? Do you know what you had in mind there? I can't think of it. Okay, we got the sense of it here. So here's the new post state. And so I want to ask, like, how can we generalize this beyond money, right? Like, we've used this very concrete and very useful cryptocurrency example, but actually, we don't need to restrict the UTXO model only to cryptocurrency, and generalizing it is extremely easy. Let me make that transition again. So the difference is, instead of just encoding a number, which represents the value of the coin, we can encode an arbitrary blob of data, right? So for the non-programmers, this is like a vector of bytes. It's just a bunch of binary data. And the idea is that inside of that binary data, you can encode whatever kind of rich state you want. Maybe that's a voter registration, or a vehicle registration, or a CryptoKitty, or a position in a DEX, or any number of things. And in every case, no matter what it is that you're jamming inside of your UTXOs here, the transactions are always the same. They're always going to consume some input and create some new UTXOs that are output. So I'll give a little 1-minute intro for those who don't know the game CryptoKitties. You could have these little pet kitties. They were like NFTs, and you could have it a name. It has some like cute eyes and fur color and all that stuff. And then maybe I can take my CryptoKitty and take it over to Andrew's house and breed our CryptoKitties, and then eventually, after some gestation period, we get some new offspring. So the way that that would look in the UTXO model is that in the first transaction, it would consume, like let's say my CryptoKitty and Andrew's CryptoKitty. And then what it would give back is my pregnant CryptoKitty and Andrew's not able to breed yet CryptoKitty. And then in a second transaction, it would consume my pregnant CryptoKitty, and it would give back 2 new outputs, which is my CryptoKitty original but no longer pregnant, and the offspring one. And so it doesn't matter what your state machine is, you can model it in the UTXO model. And what I'll say is that some state machines lend themselves to be modeled very naturally in the UTXO model, And other state machines lend themselves to be modeled very naturally in the accounts model. I've never encountered a state machine that you truly can't model in both models. You kind of always can, but a lot of times it's the case that one or the other is better. And so when you go to like, build your chain or your application or whatever it is, if you have the flexibility to choose your user abstraction model, you should think about whether the UTXOs or the accounts actually are better for your state machine. Oh yeah, right. Yeah, this is a perfect slide for what I just said out loud. So here's the final point that I'll make. This is something very unique and interesting about the UTXO model. The only on-chain logic is checking logic. With the UTXO model, your transaction tells it the complete input state and also tells it the complete output state. So the blockchain is never calculating the output state when you're in the UTXO model. Instead, what it's doing is taking the input state that you told it and the output state that you told it and just checking that there's some constraints that are satisfied, like the input value is more than the output and all the signatures are valid, and etc. This is a lot different from what we're going to see in the accounts model, which I'll foreshadow right now. In the accounts model, you give it some input and parameters, and the verification logic's on chain, and it computes the output. The on-chain logic computes the output. So now it's time to start getting at your question, and I'll flip it back at you. Can you see any reasons why that might be a disadvantage or advantage? Right on the end here. Yeah, okay.
I see a still account model would be easier.
Still seems easier, huh? Okay, yeah, go ahead. Do you have a mic? Somebody throw the mic right here. Tomorrow. Yep. There it is. Go for it.
Yeah, you have a predictability. You off-chain can understand in advance if the transaction goes well or not. So you release the effort on chain to do any calculation. So it's a faster, secure.
Effort on chain. Effort on chain is what I was looking for. You said something else that's true too, but I'm not ready to talk about yet. So blockchain, running logic on a blockchain is expensive. Blockchains that allow you to run arbitrary logic, like smart contracts like Ethereum, they use a block space model that's based on like gas or compute time or something. And the more compute you make the blockchain do, the more you have to pay. So in the accounts model, the chain has to do all the compute to find the post state. But in the UTXO model, I'm telling it the post state. So my computer here can do all the compute, which is easy because only I have to do it. And we only pay for the minimal amount of on-chain checking, and that's what the replicated state machine does. So in that sense, it can be more efficient. So that's one advantage of the UTXO model. Oh yeah, go ahead.
I think also because the outputs are independent, you could parallelize the processing when you have the UTXO, and on the accounts base, you need to do one thing after another because you're changing the same position in memory.
So we'll make that point about accounts again once I describe it, but your point about UTXOs is exactly right. When it comes to scalability, UTXOs are awesome for parallelization. If you guys remember, I was talking earlier about DAGs, and I was explaining that it can be quite challenging in a DAG to know whether like two different transactions that are in the history conflict with one another. Well, with the UTXO model, that challenge completely goes away. Because in the UTXO model, you can see exactly which inputs are consumed by each transaction. So if I want to know whether two transactions are compatible, I just look at their inputs. If they don't touch any of the same inputs, they're compatible. That's it. End of story. And then with the accounts model, that's a little bit different because there are no inputs, basically. Okay. Oh, yeah, sorry. Go ahead. Throw the mic over here. Awesome.
So can you just go back a bit?
That one? Or which one do you want?
Whatever. This one.
That one?
Yeah, it's good.
Okay.
So like this format, basically owner value ID.
Yep.
So basically all the data about the state is stored in the value, in the hash, right?
Yeah. It's not a hash. It's actually complete data.
Okay.
Yep. Or it could be a hash, but in general, it's
data.
Yeah.
But then there's no a header, or basically maybe these are the only valid fields in the UTXO model.
Sorry, what was that last sentence?
So the only valid fields are these ones?
In your UTXOs, yes.
Yes.
So the UTXO itself has a pretty rigid structure, which might be something like this. But you have complete flexibility within this field.
Yeah,
You
yeah,
can put
yeah.
whatever you want in
Okay.
there.
Like HTTP request, for example.
Yeah. Oh, well,
Like
HTTP request.
I'm just making a comparison with HTTP request.
Like
Yeah.
how you can put
So
arbitrary
it'd be
payload
like
data
so-
inside of it.
So you have like owner and ID or like headers maybe,
Yes,
and
yes,
value
yes,
is
yes.
like payload.
Yes, I see exactly what you're saying. Yes, those are like HTTP headers. Yeah. But be careful with header because we talked about block headers this morning.
Yeah.
That's why I was kind of. Yeah. Okay. Well, one more in the back. Chuck the mic right back behind you. Oh my God. Okay, go ahead.
Yeah, so I was asking, can there be multiple inputs, right?
Yep.
Wow, so it's really good. Okay.
Yeah, thanks. Cool. I like it too. Do you have a question? Oh, okay. All right, cool. All right, let's get to accounts here. Is there a different way? Well, yes, spoiler, there is. We've mentioned it several times. There's also accounts. So this is the other way to do it. We've still got, this is our whole state, just like before. I'm showing our whole state here. But now what we see is that there's no individual coins. There's no notion of like Joshy has this coin and that one and the other one. It's just one balance. So in the UTXO model, I kind of think of it as like I have my little like, purse in my hand, and inside of my purse there's a whole bunch of different coins that are all mine. And then when I go to buy something, maybe I like take some of those coins and pay and get some change and put it back in my purse. But with the accounts model, it's totally different. You have exactly one place, and it has everything about you stored under that place. And so in an accounts cryptocurrency, I like to think of it as like I have this like cauldron of molten gold in front of me. Like the fire's always running under it to keep it molten. And then like when I want to pay you something, I like put a little heavy duty thing down here and tap some of the molten gold out and give it to you, and you don't like keep it in that cup or put it somewhere new. You like pour it into your cauldron, mixing it in with all of the gold that you already had. Because when I go to like send some of my 150 tokens over here to Pauline, she doesn't have another place to put it. The only place to put it is to add it right onto this existing thing that we have here. And so already we can see how this kind of messes up concurrency. Because imagine that I wanted to like send Pauline some money, and then separately I wanted to send Andrew some money. In the UTXO system, I can just use two different UTXOs, and it's very clear that those don't conflict with each other. But in the accounts model, we have to check each one in order to see if I have enough balance. So imagine that I try to send 100 tokens to Pauline, and also I try to send 100 tokens to Andrew. Those can't both go. Either one of them can. Neither one of them is fundamentally wrong, but they can't both go because they spend more money than I have. And so in that sense, the accounts model is kind of uncertain as well. If I send both of those transactions, we need some way to know which one has to go first. Okay, so now let's look at some transactions. We know that this, so basically what we do with the transaction is we just like say this is relevant to my account. You don't even have to say it's relevant to your account. In the accounts model, it's just signed by someone. Like the entire transaction as a whole has a signature over it by one account, and from that signature, you know who sent it. This is totally different than UTXOs. Remember I was talking about like me and Andrew pooling our money and we take some of my inputs and some of his? Can't do that here. If you want to do that in the accounts model, you have to like separately set up a multi-sig, or like I have to send him my money first and then trust him not to hose me. So that's just one other difference. And then I guess the thing that I'll say in here is that when you call an extrinsic in the accounts model, you have to send a bunch of additional information in. So look at this. I have to send explicitly how much money I want to spend. I can't just rely on that to be known from the input data, because otherwise it would spend my whole value every time. I might only want to spend like half of my wallet or a tiny amount of my wallet or something, and so therefore we have to include it in the transaction as well. Okay, so let's just talk about verification in the accounts model. So we're talking about a cryptocurrency right now. That's like always the first example because it's kind of like fairly intuitive. So first of all, when I try to send money, we have to verify that I have enough money to send. We can't send more than you have, of course. And oh yeah, wow, this is a subtle one. we have to verify that the amount that I'm sending plus the balance of the person that I'm sending to doesn't exceed the maximum like value for my integer type. So let's say I have like an 8-bit integer. There's some maximum value that fits in 8 bits. And if let's say Andrew has a lot of money, he almost has that 8 bits loaded up, and then I send him some more, and I cause an overflow that makes his balance go negative or whatever, that would be quite a security risk. And so in the blockchain, it's good to check for like edge cases like this. Now that we're here, this is reminding me, that's for sure remember when we were in the UTXO slide, and I said, like, Andrew, there's something in your speaker notes, what are we missing? This was it. Let me go back. Yeah, well, you can have overflow in Rust in release mode, at least. Okay, so in the UTXO model, you have to make sure that all of the inputs don't overflow an output value, because then you could, again, have the wraparound. So that's always something you need to check for. All right. So here's the other thing. Check the nonce of the account, okay? So I didn't explicitly define nonce in this context yet, but I did mention, I'll get you in one sec, but I did mention that we need a way to know which transactions are supposed to go in which order. I said earlier, imagine Andrew tries to send me 100 tokens and then Pauline 100 tokens. And either one is good, but together they're not good because that spends too much money. For this very reason, the account system has a notion of nonce. And every single account in the blockchain has a nonce associated with it. So when you create a brand new account, your nonce is 0. And when you send a transaction, you have to send nonce 1 as part of that transaction. And then your next one is nonce 2. And so every time that you're sending a transaction from your account in the accounts model, you're making sure that you get that nonce right. And so if the blockchain gets a transaction, let's say I send it a transaction from my account, it says this is Joshy's like 10th transaction ever, nonce 10. When the blockchain gets that transaction, it looks in my account and makes sure that that's the correct nonce, and if not, throws away this transaction because it's not good. In the same way as it's not good if it spends more money than I have. Yep, in the back.
Yeah, Marisha. So my question is on UTXO actually.
Okay.
So is UTXO transactions, is it atomic or non-atomic? As in, if one fail, for example, the sum, if we use one, the checks are okay. But then if we output that one extra, the verification fails, right? So is it atomic or non-atomic?
Yeah, it's atomic.
Atomic.
Atomic, that's
Okay.
right. And it's actually, in blockchains, transactions are always atomic. That's an important aspect of them. They either go through or they fail, because otherwise they could like leave your state in a kind of corrupted.
But then can't we modify to make it non-atomic in a way that if there is 3 outputs and if we remove one, the checks like pass, but if we include that one extra, the checks fail, and just we kind of like add addition of on-chain logic and to kind of like rebalance the stuff.
Ask it one more time. I didn't
Yeah,
quite
so
get you.
I'm saying like can't we kind of tweak it to be non-atomic, as in if one fails, for example, there's
Can you
one
fake
input.
it? Can you fake it?
No.
Oh.
If there's one input and 3 output, right?
Yeah.
But the checks are if we add the 3 output, it
Okay.
exceeds the one input,
Okay.
right?
Yep.
So, but then if we remove one of the 3 output,
Yeah.
the checks pass.
This is actually an extremely smart question. So let's go back here. Okay, so here's a transaction, right? This is a pretty simple one with 1 input and 1 output. Okay, let's pretend that there's another output over here. Okay, so I'm sending like some stuff to Andrew, and then I'll send some more stuff. Your name's Mauricio?
Yeah.
Okay, yeah. So I'm sending I'm saying stuff here because we're not in the tokens one to Mauricio. Oh, but we have to be in the tokens one for this example. So, boom, there it is. So I have my one output here and my other one here, and let's say I try to send like 65 to Andrew and 10 to Mauricio, and you're saying that's obviously invalid. We would need to throw this transaction away because it's more than 70. Now imagine like the miner or whoever it is that's looking at this thing, inspecting it, says, I would really like to take the tip from this transaction. I would like to include this one. What if I just modify it? What if I just like erase this other output? Like here's an input. It already has Joshy's signature in it, right? Let me just modify this thing, rip it apart, and create a different transaction. So that's a very clever thought about an attack, and here's the way that we prevent it. And I didn't mention this because normally this subtlety doesn't occur until you're pretty deep, so nice job. What we're signing over here, when you sign an input, so there's a signature in each input, but what you're signing is not just the input itself, you're actually signing over the entirety of the transaction in which you're including that input. And so therefore, if anyone tries to like modify the transaction by like removing an output or adding an extra one or like anything, then your signature's invalidated. And so then that check fails. Great question. Okay. Oh, yep, right in front of you.
When you mine a block, how does that look in terms of UTXO? Does it just appear?
Those are like orthogonal processes. So mining is just like earlier, you know, you grab transactions out of the pool, you put them in order in your block, and then you solve the consensus, and then so like Andrew talked about.
You get the money, right? And then like the money appears.
Well, that all depends on your state machine. So let's talk about Bitcoin. Okay, so Bitcoin is a UTXO model, and in Bitcoin, if I send a transaction like this one, there's these difference of 5 tokens, and so this goes, the 5 tokens go as a reward to the miner. But that's totally up to your state machine logic. Like you can change that. You can put it in the treasury or burn it. Or if you wanted, you could even say like that's invalid. Maybe they have to add up to be perfectly equal. That's pretty atypical that way though. Okay, yep, right up front. Right here, right here. I say you should throw it next time. I like it.
I have a question about, imagine that indeed, like you said, I've got 100 coins and I'm trying to send to 3 different people 50 coins, whatever.
Yeah.
So there is no time indication. You keep track of the nonce.
So this is about accounts, I guess, right?
Yeah, accounts. So you keep track of the numbers, so
Yep.
8, 9, 10.
Yep.
Is there any way how you could predict which one goes first? Is it then 8 and then 9
Oh, it
and
always
10?
has to be they have to go in order.
Oh,
Yeah.
okay.
So like so you as a user who's sending a transaction, you should just send them in the order you want to go, 8, 9, 10. As a miner, let's say like for whatever reason, network latency or some weirdness, they like get your transactions out of order. They get like transaction 9 first. They'll notice that in the mempool. They'll know like this transaction doesn't have the right nonce, so if I include it now, that's gonna waste block space and waste me time. So what they'll do when they get your transaction out of order is maybe they'll just throw it away. That's the easier one. Or a lot of times what they do is hold on to it for a little while to see if some other transaction will come in to make it valid. So like if I see your transaction 9, I'll just be like, okay, let me set that aside, that's weird. And then here comes your transaction 8, and I'm like, now it all makes sense, and now I can include both of these. Yeah. Okay, great questions. So I think we're about done here. Yeah, and let me just reemphasize right here, do the actual computation of the output values. This is in our verification rules. How silly is that? We're actually computing this stuff on chain. We're actually doing all of the computation on the chain. Okay, so I've railed against the accounts model pretty hard here, and I'm going to be honest with you. I've tried to take a little bit of a UTXO friendly perspective because in the Polkadot and Substrate ecosystem, it's almost entirely accounts. And so for the next 3 units, or maybe even more, you're going to be learning a whole lot of details about accounts. So I wanted to make this one a little bit more UTXO-y for you guys. But let's talk about some of the advantages of the accounts model. Do you want to go first? Tell us. Get the mic.
Yeah, I see the more parallel transactions, no racing condition. That's the greatest. Option computing is advantageous. So that's just two very strong reason I have now.
Yeah. So let me talk about the race conditions. This is the one that's most compelling for me. This is what I think is coolest about the accounts model. So imagine that there's some system that you're interacting with, and a lot of people want to interact with it. Maybe it's like a liquidity pool or something like that, some kind of like on-chain financial instrument. And let's say there's like, okay, I don't know, let's make it really concrete. Like let's say it's like a Bitcoin versus ETH like swapping pool, like automated market maker or something. And so the way it works is that any user who wants to trade Bitcoin for ETH or vice versa can come and submit a transaction and say like, okay, here's my Bitcoin, just please credit my account with the like corresponding amount of ETH or vice versa. And so in the accounts model, anyone can queue up their transactions to interact with that DEX in any order, okay? And let's say like, your transaction comes in first and then mine comes in. They can both go with very little consequence. Now there may be some consequence, like if you go first, maybe you'll get a better rate and cause some slippage and I'll get a worse rate. Whereas if I go first, I get the good rate and cause the slippage and you get the worse rate. So what I'm trying to say is that in the accounts model, you don't have to synchronize with other users about who gets to use the app in which order. That can happen automatically. But there's a downside to that too. Let's say I see the state of the DEX and I say, okay, they're offering like this conversion rate between Bitcoin and ETH. That's a fair price. I want to use this pool. And I create my transaction and I send it off into the transaction pool. But in the meantime, yours goes in first and it changes the state of the pool. And now the rate's not even what I thought it was. And then my transaction goes in and I do the swap for a different rate than I intended. So this is one of the weaknesses of not being able to specify your exact pre-state. So let's see how that would work in the UTXO model. So in the UTXO model, you would think of one of these as like the state of the DEX itself. It has, we need the opaque one, I guess. Where is it? It's got to be here. Boom. Okay. Let's think about this one as the state of the DEX. Encoded in this like rich state blob of bytes is all the information about the current exchange rate and how much is in the pool and everything. And I see that and I say, ooh, that looks really nice. I would like to interact with that pool. So what I do is I create a transaction that consumes the current state of the pool as well as the Bitcoin that I want to put into it. And what it outputs is a new modified state of the pool and the ETH that I'm going to get in exchange for my swap. Now, if you send a transaction at the same time wanting to interact with this pool, and mine happened to go in first, on the one hand, that's a pain in the ass, because now you have to make a whole new transaction and start over. But on the other hand, that might have just saved you, because I might have affected the rate to a rate that you didn't want to use anymore. So the UTXO model is deterministic in knowing exactly what kind of state you're going to take in as your input state. And if that input state doesn't exist, then your transaction doesn't go. Some people think of it as non-deterministic in the sense that when I send a transaction, I don't even know if it's going to make it in because I might be racing with someone else to consume that input.
So we could say that the UTXO is good when users consume different outputs. But if they want to consume the same output, then the accounts model is better.
Yeah,
it's more parallel. You can do it more in parallel.
Yeah, I think that's a good like first order way to say it. I would encourage you to avoid the absolutes of better, because I think that typically for this kind of like automated market maker, accounts are better because it's totally unrealistic for a whole bunch of real world users to be like racing, trying to get, this is why people say, it's tiny bit not quite right, but it's basically right. They say like Cardano can only have like one DEX transaction per block. That's like basically pretty close to right because of this exact reason. And that's like incredibly annoying for DEX users. But the nice thing about it is that you're not going to accidentally get like a rate other than what you expected. So I would say you basically got that down.
I didn't quite understand the concept of transaction pool. Like,
oh man, that was from this morning's lesson. The transaction pool is where the transactions go before a miner puts it into a block. So when
where like on chain, like
it's off chain. Nope, it's off chain. So every node in the blockchain network maintains their own copy of the transaction pool. And then, Andrew taught you guys about like the leader election mechanisms. Let's say it's like Aura. So we're going, here's our 5 authorities. It's you, then you, then you, then you, then you, and then back to the beginning. So like, whenever it's his turn, he just looks at his own local private copy of the transaction pool, grabs out some transactions, builds a block, and ships the block off to the network.
Okay, but then these
are outputs. This is far away from the transaction pool. This is inside of the state of a state machine.
Yeah. So okay.
Okay. Yeah. That's good. Oh, you have a hand. Oh, okay. We have so many hands. Let me check the time real quick. Okay, it's been almost an hour, so I'll take like 3 more, I guess. Go ahead.
Someone was asking me about mempools yesterday, but I guess for clarification, each node's mempools is different from other ones, right?
Okay, hold on.
It's all based locally, right?
Let's get accounts and UTXO questions first,
Yeah.
and then I'll do other ones afterwards. Okay, in the back, one in the back. All the way back there. Check that one back there.
I have a question about UTXOs. Like, I understand their parallel nature, the possibility to modify multiple them in parallel, and they kind of make sense for DAGs. But why are they like used in blockchains when blockchains have total order of events? And the other part is when we mentioned like they don't have the execution logic, they have just the verification logic because you provide the output and the input. Like, why would the verification logic be any like less computationally intensive than the execution when, like for instance, when we're moving funds, like in both the account model, we are just doing like an addition or a subtraction, and here the verification would be the exact same operation.
Yeah. So in the case of a transparent cryptocurrency, it may be that the verification versus computing the end result isn't so much different, because that's like pretty like arithmetic kind of stuff, you know? But is a whole broad class of problems where verifying the computation is faster than doing the computation. And actually so you guys that might have rang some bells. Has anyone ever heard of like a zero knowledge proof, for example? So if you want to make a privacy coin, this is the way to do it absolutely for that very reason. Yeah, and I think, just thinking about it on the spot, I think you're right that in the case of this cryptocurrency, that's like it's not such a big deal in that case. Yeah. Okay. Any others? Yeah, over here.
Hello. So let's say if I'm transferring money to India, which I usually do, I can fix a bank rate because I know the banker. Similarly, in the UTX, I understand that in UTX, if the state doesn't match, my rate changed and that would not go through. But if there's a smart contract in between on Polkadot that says I fixed this rate here, then the transactions will not go through even in the account.
So I didn't totally understand it, but definitely Polkadot is accounts based.
Yeah.
So what was your question about the accounts?
So if I'm saying that I don't get that $70, 70 rupees to Indian, like Indian rupees to $1 or something like that,
Yeah.
that rate changed on the fly, and I have put it in a smart contract, it would still apply. Like transaction will still not go through because rate changed.
Okay, yeah. Maybe let me see. I think maybe what you're saying is that like a lot of automated market makers in the account system have built this additional feature to like mitigate the effects of this like sequential interaction with it. So in addition to specifying the like really fundamental stuff, like how much Bitcoin I want to put in, I also can specify like, here's the worst case rate that I would get. But if you think about it, like whatever you say is the worst case rate you'll take, you can pretty much guarantee that that's what you're going to get. It might feel like, oh, maybe it'll be this bad thing, but maybe it'll be better. Hopefully it'll be better. It's a better rate right now. It's not going to be better. Because the moment you put that transaction in the pool, someone's going to see it and someone's going to front run it. They're going to trade with the pool to make the rate as bad as you're willing to accept, then put your transaction, then undo their original transaction, and like, yeah, that's called a sandwich attack, and it's an example of maximal extractable value. Thank you for bringing up that feature. So that's actually a really good point too. So like I said earlier, you can usually build your dApp in either model, and that's like a good practical way to like make a DEX really work well. And I was gonna say like, hopefully it's pretty clear by now that like these Uniswap style, AMM style DEXs are way better in the accounts model. Well, an order book DEX is way better in the UTXO model. So that's like what I think of as like the pinnacle example of like similar systems that work better in accounts or in UTXOs. So like a Uniswap AMM versus an order book. Is this about accounts and UTXOs? Nice. All right, go for it. Who's got the mic over there? Yeah, there it is.
Just a question, maybe regarding the general benefit of using UTXO. There is saying the general computation-wise, UTXO is better compared to accounts model. But my first impression is like UTXO is more like Bitcoin and all the proof of work.
Oh, okay. Don't affiliate it with proof of work. Like, it's true that historically, like proof of work and UTXO were in the early generations, and now post Ethereum, there's more like POS and accounts, but those absolutely do not need to be correlated. It's totally possible to build UTXOs with proof of authority and accounts with proof of work. They're they're not like married up or even correlated.
So in terms of computation, we are saying that more computation consumes more power. So on the contrary, it's like I can still use UTXO model on energy saving.
Oh, yes. Okay, and also let me make this, so you're thinking about it from like an energy perspective and like total energy use of the network. So I made the case earlier that the accounts model typically does more computation on chain, and that's true, but this is orders of magnitude different from like the proof of work energy consumption. So if you're worried about energy for like environmental reasons, worry about the consensus layer and proof of work. Don't worry about the accounts until you're ready. You know, it's like a totally different order of magnitude.
So just separate the consensus energy consumption. And now we're talking about the account.
I mean, have you seen those graphs that are like showing Ethereum's post-merge energy usage? You know, they show like, okay, here Ethereum started and the energy went up, and then we did the merge and now it's down to like nothing. Well, Ethereum was still accounts model and is still accounts model post-merge. So that shows you like how much of the energy was used on mining versus accounts. So when I'm talking about like the difference in computation between accounts and UTXOs, that's not for energy or environmental purposes. That's for like block space purposes. It's for block space is a limited resource and it gets expensive when you like fill it up purposes. If your concerns are environmental, then just don't use POW, but accounts are still fine. Okay,
Hi, Joshy. One question. I don't understand how is the mechanism that is used to synchronize the validators, because I'm thinking, for example, let's say you are a validator and Alex too, and I'm an attacker.
You're what?
An attacker.
Okay. Oh, yeah. That's what I was thinking. You're an attacker.
And then I have a wallet that I have copied, and then I maybe I have 200 dots. So I say I'm going to send 200 dots to him and to him.
Yep.
But then I send the transaction. So this transaction, there are two transactions.
Yeah, two separate transactions.
Separate.
So it sounds like you're doing a double spend, right? You have tokens and you're sending two different transactions that both spend them.
It could be managed by the two different validators.
Yeah.
So if this is going to be received and go to the back of transactions, you begin to verify, and eventually you are going to say, okay, this transaction seems legit, and also Alex will say, hey, this transaction seems legit.
Yep.
And then the transaction is confirmed. So how do the validators get synchronized? Because you say that the error, it takes 1 day or something like that. So the block is not still delivered, not from you or not from Alex.
Yeah, okay. This is a great question, and I'm going to go back to my earlier slides to answer it, because this is not so much of like an accounts versus UTXOs, and then I'll use that as a transition to let mempool people ask questions too, okay? So this is a good one. There it is. Blockchain structure. Okay, actually, hey, this is actually a good one right here. So you have some blockchain, you send two transactions, either one is valid on its own, but they can't both go in the same history. And not only that, but you do this clever thing where you send one of them to me, a miner, and you send the other one to Alex, also a miner. Now, most of the time, one of us is going to author a block first, and the other one's going to import it and just roll with it, right? So like, let's say we were here, you send us both a transaction, I happen to solve the proof of work first, or I happen to be selected by Aura first, and I author this block, Alex sees it, he imports it. Whenever it's his turn, he builds on top of it. And by the way, it's not like just because you sent him a transaction, he has like some emotional connection to it. Like the moment he sees my block, he's like, oh, well, this one that was in my pool is junk now, so throw it away. But it can occasionally be the case that you perform this attack like right around this time, and either by luck in proof of work, or maybe because we both have a low enough VRF output in Babe, Alex and I both author blocks. And now like your one transaction is on this side and your other transaction is on this side. And now you're maybe getting close to successfully executing your double spend. But at the end of the day, all you have to do is wait enough, because this is going to be eventually consistent. So like, let's say we just see these first 4 blocks, Neither chain is longer, right? So we don't know which one's the real one yet. All we have to do is wait till the next slot. Then this one comes out. Now this is the longer chain. Now whatever transaction you sent to me and I put down here, it's off. It's orphaned off. It's reorged away.
Okay, but if in the example that you say that you were selling a car, then I could say, hey, look, the transaction has been done, and it's not still connected to the main
This
blockchain.
is a double spend. You're describing it exactly. And there's a lot that goes into it. There's, first of all, everything you've already done about sending different transactions to different validators, blah, blah, blah. But what you really need to do is, like, you need to get a transaction in here. And if you're selling a car, people aren't going to be like, oh, it's in the first block, here's my keys, see you, never. You know, they're going to be like, okay, let's wait like 3 or 4 or 6 or 10 blocks deep. Or if it's proof of stake with finality, they'll say like, wait till finality, then you can take my car. But if you can manage to do this somehow, if you can get your transaction deep enough, or if I'm in enough of a hurry that I'm like, all right, here's my car, see you later, and then you have enough mining power to cause the other one to eventually become the longer chain, then you just double spent me and stole my car. So seems like you understand that, so everybody watch your cars.
Okay.
Do you want to ask your mempool question? Or do you want, yeah, okay, good. Yeah, chuck the mic up here. All the way up front, yeah.
Yeah, so in terms of mempool, I think you mentioned that each node has a copy of the mempool.
Yeah.
But I mean, really, technically speaking, right, different nodes in the network have different versions of the mempool.
Yes,
because,
exactly.
So it's not like the same.
They all have their
right?
own view of the mempool,
just-
yep.
Okay.
Yeah, oh yeah, that's a great question. Okay, I probably could have answered that earlier.
Yeah.
Thank you for your patience, yep. Just like the blockchain itself, they all have their own view of the mempool. And a lot of times they're like mostly the same, but it's almost never the case that they're totally